This is bonding video number 8. By the end of this video, you should be able to describe the properties of metallic bonding. To do this, you need your bonding video number 8 worksheet and a pencil. Every definition we have had so far about a bond has started with the words electrostatic attraction. Metallic bonds are no different. They're going to be an electrostatic attraction between the cations and the delocalized electrons. Now, what does this mean? Cations are positive ions. Metals make positive ions. If you look at your periodic table, the metals on the left are going to be +1, +2, or +3. Delocalized electrons means that the electrons are able to move throughout the substance and they do not belong to any one specific localized region. They can spread throughout. This is sometimes called a sea of electrons. When it's done, it's going to create a lattice structure similar to the ionic compounds, and it's going to have metal atoms only. The reason why is the negative charge will not be another ion from another atom. It will be the electron. Now, an example of this is the silver ions. The silver ions here, you can see, are in the same areas as the electrons. The silver ions make a nice lattice structure, very much repeating, very uniform. But the electrons, because they're so tiny, are free to move and go in between the spaces in between the silver ions. As long as they're close to a positive ion and not close to a negative ion, this will work. The properties that metals have are caused by their delocalized electrons. Two properties are that they are ductile and malleable. Ductile means that you can make it into a wire. You do this by drawing it through or pulling it through a small opening, so that what comes out the other side is a wire, the same size as the opening. They're malleable because you can pound them or beat them or smoosh them into very thin sheets. For this, you want to think about aluminum foil. Aluminum foil is a very good example of the malleability of a metal. As you know at the store, they're very thin, and you can actually bend them over the dish, the plate, or whatever it is you're trying to save. Now, why does this happen? In order to make these into small, thin sheets, you need to push down on it, pound it, hammer it, so that the silver ions squeeze in between other silver ions. Now, this cannot happen for ionic compounds, because when the positives get side by side, they're going to repel. But in this case, because the negative electrons are so tiny, they can fit into those little regions in between the positive ions. And when they do, they allow it to continue to be a repeating structure of positive, negative, until you get to the end. Ionic compounds can't do this because the negative ions are just too large to squeeze in between the positive things. Metals are also going to be good electrical conductors. This means electricity can flow through them. In order for electricity to flow through anything, it has to have free moving electrons. Metallic bonds are the perfect example of this. They're also going to be insoluble, meaning that they won't dissolve in anything that's polar or non-polar. Now, while they can mix with other metals, so you can get two metals side by side, the metals are so well attracted to the delocalized electrons that it's almost as if they won't let go of the electrons in order to become attracted to the polar or the non-polar solvent. They would rather stay close contact with the delocalized electron and therefore leave no room to come in contact with polar or non-polar things. But if you think about it, metals don't dissolve in water. We create bridges out of steel, and they do not dissolve in water. We have gold jewelry, it doesn't dissolve when we take a shower. And the same thing would be true about anything non-polar. Non-polar things are things such as fingernail polish remover. Once again, you don't have to worry about your jewelry dissolving in the non-polar solvent.